Good morning, Scott here, known as Cantaloupe to some online, and I'm bringing a subject to you that's interesting to me. It might be of interest to you or someone you know. And I want to cover wave function collapse. That is a piece of quantum physics that is pretty well understood by now by quantum scientists and physicists. I want to talk about what I understand, which is not a lot, to be honest, but I do know something that most people don't, I think. And I want to clarify for their interest, if they have it. The question of light, the nature of light, has been around for forever, since antiquity. Humans have been asking about light, the nature of it, what is it, what are its properties, and I believe that a large part of the interest in quantum physics and mechanics by scientists to this day surrounds answering the question of the nature of light. I think that probably pulls them into the field, and then they learn other things and it gets interesting. But there's some very famous properties that have been verified at this point that a lot of people just still aren't aware of in regards to the question of light and the nature of it. Einstein correctly predicted some things, and I want to cover those very quickly for background. He understood with his equations that as you approach the speed of light, you being any body of mass, any physical mass, two things happen. Notably, more than two, but at least two things happen. And that is, for one, your apparent length in the direction of travel begins to shrink relative to an observer. That's the first thing that happens. So you get shorter in that direction. The other thing that happens, notably, is that time dilates. It does the same thing. Time begins to slow for the body in motion at relativistic speeds. So now here's the interesting thing. As a body of mass approaches the speed of light, it can never quite get there, because if it did, it would reach infinite mass. It would drop out of this universe completely into its own reality, its own spatial compartment known as a singularity. So when mass becomes sufficiently dense and massive, which can be just due to having tons of mass, such as in the case of naturally occurring black holes and stars that have collapsed, or when any amount of mass is accelerated to relativistic speeds and thus gains mass, it can drop right out of this universe. It creates a clone of this universe. That's what happens. But that's not really the point of this video. The point of this video is about light, the nature of light. And there's a very interesting thing about it. That is, if you think about a photon as being either a wave or a particle, because this is the main question that's been going around. Scientists have continually tried to answer this question. Is light a particle or a wave? Because it behaves as both, depending on the circumstances. There is a famous experiment called the double slit experiment, which proves that light is sometimes a wave, as shown by interference patterns. When you shine light through the slits, the presence of interference patterns on the surface beyond the slits is plain. It's easy to produce this effect and to reproduce the experiment. So we know that sometimes light behaves as a wave, but then again it behaves as a particle. This is also observable. And so the question becomes, how can it be both? Enter quantum physics. Quantum physics actually has an answer to this. Many scientists have described this with mathematics and in plain language. There's something called the wave function collapse, where your particle becomes a particle after the wave function collapses. It becomes particle-like. And the real interesting thing, if you consider that, remember, when you're traveling at relativistic speeds, time slows down. This is a difficult idea. Bear with me. As you approach the speed of light, that is, the speed of a photon, time slows down until at which point, when you reach the speed of light, time stops. So what does that mean from the perspective of a photon? Consider this. Think about this for a second. A photon traveling through space, from our perspective, and from its own perspective, how long does it take to get there, wherever there is? Hear me out. How long does it take that photon to get there from its own perspective if time is stopped? It's already there. And the real interesting thing is, if the photon is always already there, how many photons are there? There's only one. There's only one photon in all the universes. And that's the real interesting thing. And it's already there, no matter where it is. Reach out with questions or comments to whitehotrobot@gmail.com. Thank you.